Have you been reading in the chapter on Scholar? You find it any useful or any good? Any comments, any feedback? All right. So any questions so far? (4104), you got the information about the lab, everything is okay? No problems? All right. So we've been talking about the circle theory, or circle approach to solving transmission lines, analysis of transmission lines, and we decided that we're going to look at a very simple case, which is the signal propagation in one direction. In other words, we have only one source on one end, and the other end is indefinitely long, so nothing is traveling in the opposite direction. And we looked at that, and from that we were able to extract some physical insight of the parameters. The solution gave us a few complex parameters that came from the equations, like gamma and Z naught and V plus and V minus. So we looked at gamma and we discovered that it has two components, one real and one imaginary. The real part was an indication of the rate of decay of the signal, so we call that the attenuation coefficient. And the beta was a phase parameter, a phase constant, that indicates how the phase changes with position. So the beta was the phase constant. And we discussed the units for those. And then we looked at the solution for that particular case in the time domain, and we saw a wave that is traveling in the positive Z direction. That's the direction that we assumed to start with, because we assumed the source was on the Z is equal to 0 side, and the propagation was on the positive Z. And the phase velocity was omega over beta, and I refer you to the chapter in Scholar to for the proofs of some of these things. I didn't prove everything on the board, right? So you need to go and check the proofs there, and if you find it missing or you don't quite relate to it, you come back and ask me. Right? So the phase velocity was omega over beta, which indicates how fast does the phase travel or change in the positive Z direction. That was the phase velocity. We also defined the wavelength, which is the distance between 2 points of similar phase. So as the wave moves, any 2 points of identical phase or similar phase are going to be lambda apart, or 2 lambda, or 3 lambda, or 4 lambda. So the minimum distance is lambda and multiples of that. So that was the solution that we saw in the in this particular case. The solution that we discussed was only for the voltage wave. So we wrote only the V part. So the solution was V of Z and V plus V to the minus gamma z plus v minus e to the plus gamma z. And the solution in the time domain, v, z, and t, was v plus magnitude cosine omega t minus theta z plus v plus v minus cosine omega t plus beta z. We didn't do that part, we just did the half, I'm sorry. Well, anyway, plus v minus. That's an extra step here. So what we did only, we looked at this part. I guess this second half is logical. You can simply write it there if you want to. We said if we only have that part, obviously that is a complement part. If you look at the bigger picture with that, obviously you will get that part, right? But for now, what we did was only look at this part below, right? We assume that the line goes indefinitely and nothing is coming from the other side, right? We've got some control of the traffic, and traffic goes only in one direction. Now, we explained what beta was. So we C phase was omega over beta, and lambda was 2 pi over beta. Right? That all came from the examination of the time domain solution. And we said V plus still will not be determined until we put on the boundary conditions. So will be the case for V minus. Now, if I want to write the current, which we didn't get to, I of z, the solution was 1 over z naught, the general solution of V plus e to the minus gamma z minus V minus e to the plus gamma z. That was the general solution that we derived from the differential equation based on doing the KVL and KCL and solving the simultaneous equations and all that. We reached that solution where reminder of gamma was the square root of r plus j omega L times g j omega c, and z naught was another constant which was square root of r plus j omega L divided by g plus j omega c. So z naught is that constant. We were able to get some physical insight into this. So physically we saw this, and we saw how it relates to R, L, C, and G, and eventually what would be the gamma values for lossless and low loss. These are the two cases that we decided to discuss. The high loss we said we didn't discuss. We said if you need to, you can. We discussed these two. It's not really in our domain of interest at this point. But we didn't do this one yet. But we started. We said this is a complex quantity R naught plus Jx naught is equal to that square root of the complex numbers. So if I were to do lossless, that will be the square root of j omega L times j omega C, which is going to be divided by, which is the square root of L over C. So that results into R naught is equal to square root of L over C, and X naught is equal to 0. Right? These are so far our constants, parameters that came into the solution. Right? We need to look at the physical insight of that at this point now. Because I had a question at the end of the lecture, which is well justified. If this is a lossless line, how come we have a resistance and we don't have a reactance? Well, if you look at this as a resistance, as a physical resistance, obviously you are giving it more than it deserves. This is simply a constant proportionality between the voltage and the current, right? So the fact that it is real, that means the voltage is in phase with the current. That's all it means, right? It doesn't mean a physical resistance in our transmission line by any means, because the line is lossless and we have no losses whatsoever. So all what we're getting here now is, if you look at this solution, now we're looking again at this part, right? We're looking at this part, we're not looking at this part. So if you look at V of Z divided by I of Z, I get what? I get Z naught. And in the case of lossless, that is equal to R naught. In the case of low loss, we said, if you remember last lecture, we approximated that also to R naught. There wasn't much of a change, right? And we did not discuss the high loss again. High loss is not in our interest at this point. We'll leave it as a question mark. It's not in our interest. So all what we are saying here now is your voltage wave and your current waves are in phase. That's really what that means. That's what R naught means. So the physics of that is just a constant proportionality between the voltage wave and the current wave, and they are in phase. No phase change between the two of them. We'll learn later that this Z naught is what we call the characteristic impedance, and it's a characteristic number for the transmission line. Okay? It's a descriptive number. It's not really, again, a resistance of any means. It's a descriptive number that gives us a feel of what this transmission line voltage and wave and current wave behave like. If you look at this ratio here, and go to a coaxial line, for example, and you derive the expressions of R, L, C, and G based on the physical dimensions, which supposedly you have done in 3106 or 3105, and both of them actually, more than 5, the capacitance and the inductors are parameters of the dielectric constant epsilon, the mu of the media, and the radii A and B. All right? So this one here will be a function of epsilon, mu, A, and B. Function of those dimensions. So if you change your dimension, your R naught is going to change. In general, the whole Z naught is going to change, because if you look at the general expression over here, if you change A and B and epsilon mu are going to change. Obviously, in this case here, if you want to talk about lossless versus loss, you have conductivity sigma here like this, and you get epsilon complex here. So in general, you can make this a complex, and you can add the sigma of the conductor. Okay? To make it a general case. In the general case, your Z naught is a function of the material and geometry. Right? That's all material and geometry. And so is gamma, material and geometry. So material properties and geometry will decide for us how much is Z naught, how much is gamma. Okay? So if I have one line, without exciting you for anything, I can tell you how much is Z naught and how much is gamma. Because it's a function of all that. Assuming, obviously, we're talking about linear systems. Right? Now, linear, obviously, the signal strength may change the parameters of the material, and therefore you get some more complicated expressions. So if I look at any cable around the room, supposedly, knowing what material is made of, what geometry does it take, we can determine its R naught, Z naught, and gamma. And therefore, characteristic numbers are known. So you can tell how much loss per unit length, how much phase constant, what's the phase velocity, and what's the characteristic impedance. Obviously, that is at a given frequency, right? I forgot to mention that. It's logical, but it has to be written as well. For completeness, omega also comes in the mix here, because that will change from one frequency to another. So, material geometry and frequency. For completeness, I should write that. If nonlinear, then signal amplitude will come in as well, right? But for linear, signal amplitude doesn't come. So Z naught is a characteristic number, right? And the famous numbers for coaxial cables that exist in the commercial world are 50 ohms and 75 ohms. 50 ohms is usually used in laboratories and test equipment. 75 ohms is typically used in the cable TV industry, right? There are many other numbers. When you go to the lab, you will see we have a piece of cable that is 93 ohms, for example. That's another characteristic number. All these are standards that were adopted for some reason. And that probably would be a good question. Why 50 ohms? All right? Why not 25 ohms? Okay? Why not any of the other numbers that you can think of? So that would be, why does the cable TV industry chose 75 and not use the 50 ohm, which was more common in laboratories, for example? So all these are good questions that you probably can do some research on, and we can discuss at some point. But after you do your own research and you come back with some questions and some thoughts about it first. So that's a characteristic number. It tells us how the shape and the material and all that beside that. And it's basically the ratio between V and R. Okay, so for now, let's talk about what happens. Let me see what, I guess with that I covered. You have any questions at any time, stop me please. The physical implications of RLC and G and all that. Let's get an example with boundary conditions, so we will have a feeling also for how V plus and V minus are determined. Okay? So again, I'm going to use the same exact simple case here, which is this one here, right? Only one wave traveling. And therefore, in this case here, I only have one boundary condition. Obviously, when I go to the general case, I'll have to work with both ends. But for now, let's assume now that I have, whatever I have in the source now has been simplified to this. The source could be a very complicated circuit, could be another transmission line, could be whatever, and I simplify it by a Thevenin's equivalent, all right? A Z Thevenin's and a V Thevenin's. So we call the Z of the source end. What notation do I use? Do I use sub S? Yes, I use sub S. Z sub S of the source and V sub S of the source. And here's my line, which I assume that there's nothing coming from the other end. So this is my Z is equal to 0, and Z goes this way. That's my coordinate system. And anywhere here is my plus minus V of Z, I of Z. I can do that in the frequency domain with comfort. I can always switch back to the time domain whenever I need to. We know the rule. Multiply by e to the j omega t and take the real part. Okay, so at Z is equal to 0, that's V of 0, and that's I of 0. And I can write KVL for this loop here, and therefore Vs is equal to I of 0 times Zs plus V of 0. Right? A very simple boundary condition. At the same time, I have V of 0 is equal to Z of 0, I of 0. Right? This expression is right there. I can replace that by Z is equal to 0, and I have that, so I can redo this one here. Or I can redo this part. I can write this as V of 0 divided by Z of 0. It's the same thing. So from there I can find my V of 0. V of 0 is Vs divided by 1 plus Zs over Z0, which is Vs times Z0 divided by Zs plus Z0. Very simple expression. I get V of 0. If I have V of 0, can I get V plus? Well, looks like it's straightforward because V of 0 is equal to V plus, right there. So if I put Z0 here, I get V of 0 is equal to V plus. E to the 0, which is V plus. So it's actually my V plus. I got my V plus. This is one of the simplest cases that you can ever deal with, and it comes out very smooth. And we know my V plus, so I have the full solution now. My V plus seems to be a voltage divider of Vs between Z0 and Zs. Right? And guess what? Makes sense, because when you look at this expression here, V of 0 over I of 0 is equal to Z0, that means the ratio between the voltage here and the current there is Z0. So this is, by Thevenin's equivalent, is like a Vs, Zs, and if I replace this by one impedance, the voltage over the current here is Z0. We call this one here, if you stand at some point in a network, if you stand at any point in the network, and take the voltage and current at that location and divide voltage over current, you get what we call the driving point impedance of the network. That's a circuit theory definition. You go to any circuit, no matter how complicated it is, and you come at some point here, and you look here, and you look at the voltage and the current within the network, you get here the driving point impedance. Driving point impedance. So if I look at the transmission line, the input impedance here at this point, or the driving point impedance, is actually Z0, right there. As Z is equal to 0. But you see, the driving point impedance anywhere on the line is Z0. It's not just at the input side. The simple case of one source of traffic one way, no signals in the other direction, no waves in the other direction, gives you a uniform and constant impedance throughout the whole line. So sometimes we define the Z0 as the input impedance of an infinite line. Because that infinite line is the one that we're discussing right now. The line that doesn't have any reflections. Right? So that's another definition. One definition was related to RLC and G. It's defined by the parameters of the line, the geometry, and the material. And the other definition is, which is derived from the physics of the solution, it's the input impedance of the line if it is infinite in length. There is a third definition, which I'm going to show you in a minute. If this is my line here, let me erase this part. And say the input impedance at any location is Z0, right? That's what we just concluded here. Anywhere you go on the line, you stand right there and you see Z0. V of Z over I of Z is Z0. So if I replace this part by Thevenin's, and here's the rest of the line, so it's a finite line now, right? That's a finite line, it's no longer infinite. I cut this part of the line and replace it by its equivalent impedance. Here's my source, and guess what? The input impedance here is still Z0. I didn't change anything. All I did is I replaced a Z0 by Z0. and replace this part, which was Z0, by another Z0. So the input impedance of a line terminating the Z0 is Z0. So that's a third definition for the characteristic impedance. It's the impedance that is, if you were to terminate the line into it, it would be also the input impedance of the line. It's a complicated definition, but it works as well. So any finite line terminating Z0 will also give you Z0. Okay? So these are several ways to look at Z0. That's your impedance or characteristic. That's why it's a characteristic number. It's unique for this particular line, for this given dimension, for this given material at that particular frequency. The characteristic is 50 ohms. So if you terminate in 50 ohms, it will look like 50 ohms here. And that kind of situation is what we call the match termination. If you terminate in 50 ohms, your signal will go indefinitely. Where will the signal go? It will get absorbed here, and nothing will come back. Right? It's just like when they design anechoic chambers or acoustic rooms for recording and high quality sound. If they make walls like this, sound waves will bounce back from that, will cause echo and issues and all that. So what do? Is they try to build air walls. How can you make an air wall? Obviously there's no such thing as an air wall, right? So they come up with special material that they build from it that basically absorbs the sound waves and never come back. And mostly it's made out of loose fibers that the sound wave get to scatter around and never find their way back in the fiberglass and many other things like that. Mostly fluff material that's close enough to air that the signal goes in and doesn't come back. So this is here going to be the same value of, so this is 50 ohms, all you need is just a pure resistance of 50 ohms that will absorb your signal, nothing will come back. Let's now look at signals coming back. We said earlier that if the signal is traveling in the opposite direction, we get the same exact result, right? Physically, it doesn't make a difference, right? So if you flip the board or turn around, whatever, whichever way you look at it, it's the same kind of thing. So if I put my source here instead of there, you know, the story physically is the same. So basically, if I were to make this a V minus solution instead of the V plus, let's make that a V minus, that's going to be plus Z now, because it travels in negative Z, so it's V minus, that's a plus, this is here P minus, the phase of the V minus, that's still the same thing, there's going to be a V minus and a plus. See, it's easy for me to just modify the board, you guys have to rewrite everything, right? Do I need to do any more modifications? That's it, same exact thing. The trouble will start when we put the two solutions together. When traffic goes both ways and you start to having collisions or accidents or interference between the two sides. So now I'm going to talk about a finite situation, a finite line, where I have, I'm going to simplify things, make only ZL. I'm not going to put a source here. Put a source here is going to complicate things more, right? So I'll just assume that the other side is only a load, no sources. And if I do have a source, suppose you don't have a source, what will you do?
Zero source. Just do superposition.
Superposition, right? What does superposition say? Well, you short one source and work with the other, and then later you short the other source and work with the first, and superimpose the two solutions. Again, that's all for linear systems, right? Non-linear is a different story. So if I solve one source in one side, it's the same tool, and all I need to do is just redo it again and add the two solutions. So one source is good enough. You don't want to complicate things unnecessarily. Because most of the situation you have communication from one end at a time, right? we can look at one commutation from one end at a time. So, solution is, I have to go back here and write both. V plus e to the minus gamma z. Forgot to do something before I get to the general solution. Okay? I want to see the voltage wave at some location relative to another. We said that this one here is actually V of 0, if you remember, right? So let's say V of Z1, V of Z2. This is V plus e to the minus gamma Z1. This is V plus e to the minus gamma Z2. It's very useful to say V of Z2 over V of Z1 is equal to e to the minus gamma Z2 divided by e to the minus gamma Z1. It's very useful to have this relationship because it tells you what's your signal like at some location relative to other locations. So that kind of formulation here is very useful, and we use it all the time. So it's e to the minus gamma Z2 minus Z1. All right? So the distance here, Z2 minus Z1, is important. You can play all sorts of games here. Magnitude-wise, that gives you e to the minus alpha, Z2 minus Z1. That shows you how much the signal attenuated. If you want to talk about phase-wise, so the angle of V Z2 minus the angle of V Z1 is equal to, the angle is what? Minus beta of Z2 minus Z1, right? So all these things are useful to keep in mind, that we can play these games and we can get the voltage here and there's a voltage there, magnitude and phase. Okay. So these are side issues. Okay, let's get back to the full solution now. Same thing with the current. You can do similar expressions for the current. So, you can stop anywhere and branch off and play all sorts of games with the expressions that we have. So now I'm going to add the V minus e to the plus gamma z. I have a situation now where both exist. I don't have a one-sided propagation. I have waves traveling both ways. Solution for I of z that we had was 1 over z naught v plus e to the minus gamma z minus v minus e to the plus gamma z. Both of them. Now we can spend 5 lectures discussing what's going on here, okay? But I will have to rely on you reading to make my job simpler because, like I said, supposedly all that is a review. Now, if I want to look at the time domain, because the time domain is going to show us some physics, V of z and t is going to be v plus magnitude cosine omega t minus beta z plus phi plus v minus magnitude cosine omega t plus beta z plus phi minus. Now the phi plus and the phi minus, these phases here, are constants and they are there for the accuracy of the expression. But for the physics, if I just ignore them momentarily, they will not make us lose much insight. So if I just ignore them for the time being, the physics is still gonna come out through. So what do I have now? I'm not gonna bother with the phi plus and the phi minus, like I said. I have a cosine omega t minus beta z, which I have, I'm gonna do this one here in white. I'm gonna do the other one in blue or something, whatever color comes in my hand here. Okay. I'm gonna do it in this color, blue. Okay? So this wave here is right there. Now, you notice I forgot the e to the minus alpha z. Okay, that's also important. Times e to the minus alpha z. And this one here is times e to the plus alpha z. The magnitude is going to change by that. So here's the white signal. Which starts with the V plus magnitude right here and goes on. And I have a blue signal which will start with the V minus and will be here the opposite direction and will do something else. This wave is changing with time this way, and this wave is changing with time this way. The picture is too convoluted to come up with some sensible conclusion. So what we're going to do is we're going to go to the frequency domain. Frequency domain is going to show it to us a bit better. I've got two phasors that are being added to each other. This phasor here shrinks in magnitude and rotates, right? That's the e to the minus alpha and e to the minus j beta. So let's assume that we start with the V plus phasor right there.